Aniruddhan, I was doing some circuit physically. So I had a voltage source and some inductor, switch, etc. So I was playing with the switch, turn on, turn off, etc. So the switch was on for some time. Then I suddenly turned off.
Okay.
Big spark.
Oh, really? Was there some coil in series with the switch or something?
Yeah.
Oh, there was?
Yeah, there was a coil.
Oh, okay. Okay. So, there was current flowing through the coil before the switch was...
I think so. So
Okay.
maybe this circuit was something like this. Maybe I think there's a voltage source. Vs. Maybe it was slightly more complicated, but I think it is something equivalent to this.
Okay.
Resistor was there?
No. Okay. Yeah. Okay.
Maybe because coil will have some resistance.
Coil will have some resistance, correct.
So let's say this I closed.
Okay.
I was watching something else and then turned off.
Okay.
So basically initially the switch was here.
Okay.
Let's say I turned off at t equal to 0.
Okay, I see.
Then I saw some fumes coming from here, or
okay,
at least some spark here.
Okay. See, let us look at, so the voltage across the inductor is L di by dt. That much we know, right?
L. So this voltage is L di by dt.
L di by dt. This is the characteristic of the inductor.
Okay.
And you said there was current flowing before. And so, if you suddenly open the circuit, no more current can flow in that. So there was some current because you opened it. It's open circuit. So now earlier there was some current flowing. Now suddenly that current has become 0 instantaneously, right? You must have thrown the switch not slowly, but you must have just opened it quick.
Yeah.
So now di by dt is actually like a very large value. It goes suddenly from some fixed value to 0. So di by dt must be very large, no?
So there is a large voltage.
Large voltage developed across the inductor. Most likely that would have sparked.
So then that insulation must have failed a bit.
Must have failed, correct.
Okay. Looks some idea I got, but let's say I want to generalize this little bit. I have an inductor, and if I am, let's say, moving switch, either closing or opening, in this case I am opening. Let's say 0 minus, how will I represent it?
Okay. So maybe we look at it systematically, right? So, but we will say maybe that, okay, so we need to, as soon as you open or close the switch, we need to figure out how to handle the inductor, correct? Okay.
So earlier also we were discussing if the switch is closed for a long time, t tending to infinity, let's say long,
correct.
It is closed for very long time.
Correct.
Then the current through the inductor, we said it
has settled, it's constant.
Yeah.
Correct.
You said it's
inductor is a short circuit after a long time.
No voltage across this. That's what you mentioned at that time.
Correct. So we need to come up with a systematic way of doing both, no?
What will be that current? It is Vs by R, no?
Vs by R. So the final value will be Vs by R.
So this is what we wrote. I of t, t tending to infinity.
Correct.
This was Vs by R.
Correct. But that would have been for the case where you closed the switch.
Switch was closed for a long time.
Switch was closed for a long time. So then t equal to infinity, not for this case. In this case, you're opening at t equal to 0.
Correct.
So t equal to infinity, the current has to go to 0, right? So I think you meant the case.
So from, so maybe this representation is not correct. So I have kept it
t equal to 0 minus.
0 minus.
Correct. Maybe we'll write it as t equal to 0 minus because it has been closed for a long time.
Since from minus infinity it was closed.
Correct. From minus infinity it was closed.
Yeah. So time wise it's correct, but the representation is not correct. So I should write T equal to
0 minus.
0 minus.
Correct.
So this is from, can I say like that? Minus infinity
Well,
to
we actually
0 minus. Whenever
yes,
you close
whenever
it.
you close it, you
So
have
there
been
was
waiting.
enough time for the current to
settle.
Means
a fixed
there is
value.
no, derivative will be 0.
Correct.
Okay.
So in fact, that's what we said last time as well. Derivative, so the current does not change, the di by dt is 0, therefore the voltage across the inductor is 0, so it's a short circuit. That's the way we kind of analyze that. So, but we need to, look at this case also, no? So what happens when you suddenly open it?
Maybe I will mark that current as I naught.
Sure.
Now I have opened it.
Now you have opened it.
So will the current change instantaneously?
So it cannot.
It cannot.
It cannot.
That's why it was trying to flow.
It was trying to change, but it couldn't. So in this case, it's parked, right? So I think the story for the student or the summary for the student is don't do like this, no? Don't, if you have an inductor, don't open it.
Correct.
Right? So it's a little bit dangerous.
There should be some path given for the current to flow.
Correct. So maybe what we'll do, we'll take a modified version of this circuit. So let us take the same network, we'll add a resistance in parallel with the inductor. Some resistance R, let us say. So that way we don't allow di by dt to go to infinity.
So you are adding a
resistance R here.
Oh.
Okay, it can be R or R1 or whatever it is.
Then you have solved my
I hope let us
problem.
see, let us confirm that we have solved your sparking problem. But the nice thing is at t equal to 0 minus, all the current will still be, Vs by R will still be flowing through the inductor because it was a short circuit.
There is no voltage across
There is no voltage across that L. There is no resistance through this new, maybe we can call it R1. So there is no voltage across R1, there is no current through R1.
Okay.
So all of this Vs by R is at t equal to 0 minus was flowing through the inductor.
So this is still valid.
That is still valid for this circuit.
So the current going through L will be still I naught.
At t equal to 0 minus.
At t equal to 0 minus.
Correct. That is correct. So now we can see.
It's a short circuit. That's what
it's a short circuit. Correct.
So that means at that instant I can show it as a short circuit with a current I naught.
That is correct. I think that's what we should do. That's right. So you can show it as a short circuit in parallel with the current I naught.
Is it in parallel?
No. It should be actually.
It's just a current.
It's just a current source.
Yeah.
Right.
Correct.
Because it's a current source in series with the short circuit.
Correct. So this will be at. Sorry, I can just replace it with a short.
Correct. And a current source. Correct.
And its value will be
I naught. So basically the direction of the current source will be the same as what is was the original direction of the initial current.
Sorry.
Correct.
So this is valid for
only at t equal to 0 plus.
Okay. So whatever was there in 0 minus will continue at 0 plus.
At 0 plus.
But from then onwards, if I want to analyze,
you have to use either time differential equations or Laplace domain. So this will only give you the instantaneous values as soon as you have changed the state of the network.
So basically you are capturing that initial condition.
Correct.
Correct?
That's correct.
Maybe I can write that here.
Yes. Yes, it is not like the inductor suddenly becomes a current source.
Correct.
For all time.
Correct.
Only for that initial
Then
condition.
it would have been, it will become a source there.
It will become a source then, correct.
But it can source only for some time.
Correct. So this inductor with an initial current I0, I0 will become a current source in series with the short circuit. Perfect.
So can I get something like this for capacitor also?
Sure, but I'm going to take a guess. Right? You said here it's a current source in series with the short circuit.
Yeah.
Shall I guess that the capacitor may be a voltage source in parallel with an open circuit?
Maybe.
Let's try.
I don't know.
I'm just guessing because capacitor inductor was voltage was L di by dt. In the capacitor current was C dV by dt. Here you have an initial current, there you have an initial voltage. I'm just guessing. Voltage source will become a current source, current source will become a voltage source, something like that. Let's try it.
But even before going there, you had introduced this R1. How will it avoid the spark?
Okay, let us look at that.
Because
there is a path for the current to flow now.
Oh, so I have opened this.
Correct.
So that means now the current cannot flow this way.
Correct. It now has to flow through R1.
Okay. So it will just flow through this.
Correct.
It will just flow this way.
That's right.
So at t equal to 0 plus across R1, will there be voltage?
There will be a voltage that will be equal to I0 times R1. So that current has to flow through R1.
Correct.
It will be I0 times R1 with a positive at the bottom and negative at the top.
Okay.
Correct.
That may be the, if we continue, if the switch is still open, then that may be the maximum voltage.
That will be the maximum voltage. After that, it will reduce.
It will reduce.
Correct.
Okay. So, because that voltage is now limited as I0 into R1, it's not I0 into infinite.
Correct. That's right.
So, there is no spark.
There is no spark.
Now, to do this, there may be other mechanisms also.
Correct.
Because now, when you have a resistor there, always, okay, when the diode, when the inductor is short, there is no current through R1.
Correct.
But till that, there will be some current through R1 also.
That is correct.
There may be better method, no?
There may be a better method as
if
well.
this is the only intention to avoid the spark.
To avoid the spark.
We'll see that later.
Yes.
Yeah. So we were going to find out what happens in case of capacitor.
In case of capacitor.
How we will go about? We'll try something similar? Or?
We'll try something similar. So, how about
so I have Vs.
correct.
So we'll close it
Let's
initially.
close it. Correct.
On this we discussed, no?
This we discussed. This will be okay. I think maybe the case we want to do is if the resistor was in parallel with the capacitor.
Or you want to add another switch here?
That also we can do. We can add another switch.
And a resistor?
And a resistor. Let's see what happens in that case.
So when I open this, I'll close this.
Sure. Let's see what happens.
So this is t equal to 0 minus or t equal to 0?
T equal to 0. That is also at t equal to 0, right?
So if this was the switch positions were like this for long time,
correct.
Then what we found was this will charge to
Vs.
Vs.
Correct.
Then this is open, this is closed.
Correct.
I think we have solved some circuit like
We have
that.
solved some circuit like this.
Sorry. C1 which has a voltage of Vs. This is
I think it's just C.
Sorry.
Correct. And we actually know the answer to this.
Yeah.
It is like Vs into e power minus t by RC or something, right? That's what we get for the
So we
voltage
had
across
expression for current, no?
current, correct.
Or voltage, both
Or
will be
voltage,
same in
both
this
will
case.
be same because there's a resistor.
So this Vc, voltage across the capacitor, was
I think it was
Vs
Vs into e power minus t by R1C.
R1C.
And you divide that by the R1, it will give you the current also.
Correct.
Correct.
Oh, when t equal to 0, it's Vs
Yes.
itself. That's the equation is correct.
Correct.
Okay, okay. So that means
So that means
just
that
replace with the voltage source.
replaces with the voltage
Oh,
source.
that's what you were saying.
That's what I was saying. That was my guess.
Okay, okay, okay. So if this is A and B, plus minus Vs in this case.
Correct. Correct.
Or should we write
Vs is right.
Vs? Yeah.
In this case, that is, it's V of 0 minus. That's what it is. So maybe when we summarize, we will use the right terminology, but here it is correct.
Yeah,
Vs.
yeah.
And then you'll have R1 to complete the loop.
So suppose if there was another resistor here,
Then it will not be Vs.
it will be some other voltage.
It will be some other voltage.
What it will be?
Let's add that resistance and see.
Let's say R2.
Yeah, R2. Okay.
Then
In steady state, so what we know is that there should be, what steady state means for a capacitor is that the voltage should not change. dV by dt should be 0.
So I will draw it as a separate circuit, otherwise may confuse also. Suppose we add R2, then this will not be correct.
Correct. That is right.
But the question is what it will be.
What it will be.
So you were saying something.
So I was saying that I have learned that if the capacitor has reached steady state,
Then it will not draw any current.
it will not draw any current.
Oh, that means I
It
can
is
open
fully-
circuit.
You can open circuit it.
Oh. Okay, I think
Maybe you can just put an X on top and bottom of the capacitor
That will do.
using some other color.
yeah.
Correct.
So it will be open circuit.
Open circuit.
Oh, then it is just the voltage across R2.
R2.
Okay, okay.
And that is just R2 by R plus R2 times Vs.
So it will be the capacitor voltage will be
We'll say Vc of 0 minus.
yeah. It will be Vs by R plus R1.
R2
Sorry, R2.
into R2.
So in general, then we'll say Vc of 0 minus.
So Vc of 0 plus. So the or at t equal to 0 plus,
Vc of
at
0
t equal to
minus
0
and
plus,
0
you
plus
replace
will
it
be
with
same.
yes, correct. That's what we want to say. Correct. At no, I think you are right. The value of the voltage source is Vc of 0 minus. This network replacing the capacitor with this is valid at t equal to 0 plus to find out the initial state of the network. Is that correct?
So the capacitor is a short then.
No, capacitor will be in parallel with this and it's an open circuit.
Okay.
And this you replace the capacitor with this at t equal to 0 plus, just like the inductor. Inductor, we said at t equal to 0 plus, you replace the inductor with I naught.
Yeah.
So we'll replace the capacitor at t equal to 0 plus with Vc of 0 minus.
Yeah.
What you said is correct, no? The voltage across the capacitor does not change suddenly. Current through the inductor does not change suddenly. In such cases, this is valid.
And again, if I want to analyze further, I should put the capacitor in series.
That is correct.
Yeah. That we have seen.
Correct.
That we have seen before.
That we have seen before. Correct.
This is only to capture the initial condition.
The initial condition. Correct. So maybe we'll summarize in a table. I think the resistor will be the same. I think that everybody knows now. We have just used it throughout the network.
Correct. So what shall we write here?
So maybe
equivalent circuit at t equal to 0 plus.
Correct. Correct.
We'll just put the element also maybe here. So we have first resistor. This guy is not going to change anyway. So
correct.
It will be just resistor itself. And then we have seen inductor.
Inductor, I think we said inductor with a...
There is a current I naught flowing.
I naught, correct.
That will be just a current source.
Just a current source of value I naught. But you know what? Suppose the inductor did not have an initial condition, initial current. Then I naught will be 0. So it actually becomes an open circuit. Is that correct?
Because the internal resistance of current source is infinite.
Is infinite.
Okay. So it's just a inductor which is just sleeping there. There is no current flow that.
Correct.
Then it's a
open circuit.
Okay. And then we discuss about the capacitor.
Capacitor, correct.
Which was charged to
some Vc or no V naught?
Because it is I naught, maybe we'll keep V naught.
V naught, sure.
So
and let's add the polarity also.
Yeah. So here also maybe we can say V naught. Suppose if you say V naught is a voltage across C.
Sure, we can say that. But we have specifically said Vc are not required.
It's very clear.
It's clear.
Let's not.
Yes.
Yeah.
We just need to show the polarity here. That is all.
So plus minus, then it's a voltage source with same polarity.
Correct.
And there is no capacitor. That's
correct. There is no capacitor. Value is
V naught.
V naught. And
if there is no charge,
it's a short circuit, no? Because the internal resistance of a voltage source is 0.
Yeah. So a capacitor which is
correct,
not charged.
Correct. This will be a short circuit. Perfect. So this will help us for any RLC network. It will help us find out the initial condition.
Oh, this is good.
And I guess eventually we should also teach them how to do the final value.
Final means?
At t equal to infinity,
Oh.
what do you replace these elements by? We just saw inductor as a short circuit,
Correct, correct.
capacitor is an open circuit. So I think they know that now,
Mm-hmm.
right? Resistor stays a resistor, capacitor becomes an open circuit, inductance becomes a short circuit at t equal to infinity. They can use that.
Whether we can use our, we know this final value theorem, initial value
Yes,
theorem.
that is true. Yes, we can use that also in the Laplace domain. So we can use the Laplace domain equivalent, find out the current and voltage in the Laplace domain, use the final value theorem. So absolutely. In fact, even these can be derived using the, I suspect, using the initial value theorem.
Correct, correct.
Yes.
We'll do now. Okay.
So maybe we'll just build the same.
So the at least what I can copy and
actually we can just do here, no?
Better.
We
I'll
can
just rearrange a bit.
Yes.
So
space
is there.
Space is there. We can just see equivalent circuit at t equal to infinity.
Yeah.
T equal to infinity.
Oh, sorry. R anyway it will not change.
R anyway will not change. Correct. Now for the inductor, so there is some initial current I naught, right?
Yeah.
But at t equal to infinity, there will be no effect of that. It will have a new final state, no?
Correct.
So that should have.
Should we go back to our?
We'll go to this circuit.
Yeah.
The final value is 0 if you wait long enough time.
That is true.
Right? All of that initial condition of I naught is all Vs by R is completely gone. It doesn't show up at all at t equal to infinity.
That's true. So how will I represent?
So we don't want that current coming out, no? We don't want that current coming out. So if you go to the equivalent circuit for t equal to 0 plus, we show that it's a current source. But we don't want this current to come out to affect the rest of the circuit.
So it should
let it circulate inside.
Okay.
I think that will help.
You have to give some
path.
Bypass. Huh?
Yes.
Oh, that's nice idea. So I have the I naught.
Correct. Yes. And now if you do this, this I naught will keep circulating inside through the short circuit. There will be no effect on the rest of the network.
Okay.
Correct.
It's actually as good as a short circuit.
It's actually as good as a short circuit. Correct. In fact, now you can see the inductor, if I naught is 0, there's no initial condition.
Yeah.
Then it's just a short circuit.
Correct.
That's what we have used, no? We have shown that there is no di by dt.
Correct.
By definition, at t equal to infinity, there should be no change, right?
Oh, then can we do for the
Yes.
capacitor also?
So we'll fill in this row also.
Oh.
So the inductance is a short circuit now. This third row is an inductance with no initial condition, no?
If
It is just a short circuit. Correct.
Okay.
Correct. And now the capacitor with an initial charge of V naught.
Yeah.
How will we represent that? So shall we say it is going to be a voltage? We don't want the effect of that voltage, right?
We can refer to the circuit.
Correct. We can refer to
you
the
were
circuit.
saying finally there will be no current through this.
That is correct. So it should be an open
Should
circuit.
be an open circuit.
Correct. Okay. So then we will represent this as the voltage source in series with an open circuit.
Yes.
Okay.
Here.
Yes.
Something like this.
Correct.
If there is a V0, that V0 will be there.
That V0 will be there.
If there is no V0,
It's just an
it's
open
just
circuit.
an open circuit.
Correct. Perfect.
Correct?
Perfect.
Oh.
So in fact, you students can use this to solve simple first order differential equations, base circuits, using these initial conditions.
So
and final
these
conditions.
we are talking all this mostly for DC circuits.
For DC circuits, correct. Correct. For AC, this is not true, no?
Yeah.
Because di by dt
It's
for
keep changing.
sinusoidal
Correct.
voltage, it will be
Correct.
changing.
Correct.
So this is only for DC.
Yeah.
That's right.
So I think that maybe they should, or all of us should remember.
All of us should remember. Correct.